A very important topic is understanding the two related but different ways of representing fields. We've already met field vectors. That was introduced at the end of chapter 22. We are now meeting field lines, and field lines is something, at least when I was in school, that you typically saw first because field lines makes more sense with, for instance, magnets. So you've possibly already seen field lines earlier in your education and not field vectors, and in this class vectors are a little more helpful. So we're going to talk now about field lines and how they relate to vectors. So first, here's a picture. We're not worrying about what's causing this field, but we're just going to talk about what's going on with the field. So these here, so 1, 2, and 3, are our lines. And so it has kind of a start and it has an end. Now, one thing in general is that field lines need to start and end on charges. But you can imagine that maybe there was a charge over here that these actually started at, but that's off the screen and you don't see it. So what you can't do is just start a line like this in the middle of your page. It's okay to have things start off the page, but you can't show ends for field lines or for field lines within the page itself. So this would be bad. So vectors are then at individual points and they have a magnitude and a direction. So vectors we already talked about. So one thing to note is that the vectors are always tangent to the field line at that point. And again, this field fills all space, but we can't really represent it that way. We can only represent it visually at certain points. So notice that the field vectors are always tangent to the field lines at that point, not everywhere, right? This vector represents that point only, and it's tangent to that spot on the field line. The other thing to note is that the field lines are more closely spaced here. That means the field is stronger. These vectors are bigger. When you get out here, those field lines are more loosely spaced, and you see that those field vectors are smaller. So weaker field, stronger field. Now, I might ask you the question of what's going on in this spot. Is the field 0 there? No, there's certainly still a field there. And in fact, I could go and I could try to draw another field line that starts to capture what's happening there. And I can't just draw part of it. I really need to kind of complete the whole thing. And it would be kind of in between what's going on the other ones. So then I have this point now. I can draw my field vector, which would be tangent, and it would be a size in between what's happening out here and what's happening here, since the spacing is in between. So even if you have just an open spot, you need to basically interpolate. You need to look at what's happening around it and fill in a reasonable way. So hopefully that makes sense. Again, we can only draw so many lines, so in general you want to have even spacing. It's not ideal that I put an extra line here and not there, since I don't actually mean to imply that the field is stronger up here. So do be careful. You want to make sure that things are as accurate as possible. So this would be a better field line drawing. You again see that now there's uniformity in this direction. So we've already shown field vectors of point charges. This is now field lines of point charges. And notice that again, there's only a certain extent of the page. So don't treat those ends as if they're real, and don't treat these two diagrams as interacting. So note that when you're close to the point charge, you have a greater density. If I draw a little box in this case, I see that I have 3 lines passing through it. If I draw roughly the same box up here, well, okay, that one had no field lines passing through it, which is bad, but that one has 1. So the field strength is weaker up here and it's stronger there. You also see that they're pointing away. Note that you really do have to draw that little arrow because otherwise you can't determine whether it's pointing away or towards. So make sure you don't forget to draw those arrows. And you can actually draw it in multiple places, right? You don't have to just draw it in one place, but make sure you don't contradict yourself. If you do that, that's really bad. So don't do that. Bad, bad, bad. Make sure that your arrows always agree, and it's okay to draw more than one arrow on a line. So in this case, you can clearly see that your lines began on the charges themselves. And note that they're pointing towards the negative, away from the positive. So we kind of say that they start from the positive and end on the negative, imagining them traveling. But in this case, these were two separate ones. So to briefly summarize the difference between field vectors and field lines, if you want to show field strength, you use the length of the vector and you use the spacing between the lines. And again, that's the difference between more closely spaced and then more distantly spaced. So you have a strong field here, a weak field there. The direction is literally just what way does the vector point, right? So points in this case refers to the vector, not dots. So the vector points in the direction of the field. For the field line, it's tangent. So this is a little trickier to interpret the direction. Now, you need to just choose some representative points. You can't draw a vector for every single spot in space. And you need to keep in mind that when you do actually see a spot and you have your vector that's actually pointing in some way, that this isn't telling you about the field here. It isn't telling you the field at the tip. It's telling you about the field at this spot in particular. And if you have a quickly changing field, that can be really important to remember, because you might start to have crossing vectors, and that's okay. It's that at this spot, it points this way, and at this spot, it points that way. There's nothing wrong with this. Now, for field lines, you have to just pick some representative lines. And again, make sure to not just start them or end them in the middle of your page. They either can end or begin at the edge of your page, the edge of your picture, or on charges. These can never cross. Again, these can cross because these are vectors that told you about a spot. But field lines can't ever cross because that would imply that they're going in different directions at the same spot in space. So that doesn't make any sense. And again, make sure they start and end on charges or at the edge of your picture. So let's do a comparison now for dipole, right? So this is our dipole, and we have field lines and we have some field vectors. You don't have to do both. You can choose one or the other based on what you think makes more sense to you and what you think better represents the scenario. I actually think that field lines work better for the dipole scenario. But you might then want to drop some vectors down if somehow you're adding this up with anything else. So you can see that the field is strongest really close to each charge and in the space in between. It isn't in this area that the field itself is 0, but it's kind of weaker. You also can see that it's pointing opposite of your dipole moment when you're on this bisecting plane. So remember that this is your bisecting plane and this is your axis. Remember that your dipole moment goes from negative to positive, so you see that the direction on the bisecting plane is opposite, but the direction on the axis, like here and here, is actually in the same direction as your dipole moment. And that was the result that we showed earlier from the field of a dipole, and you can see that that makes sense once we actually draw this out. So I hope that field lines versus field vectors makes sense. Again, it's really important to be clearly drawing one diagram or the other. It is acceptable to do both of them like this, but make sure that you're not half doing field lines and half doing field vectors on the same representation, that they are different, they have different rules, and it's very important to have that right.